I hope we have tried to solve this ongoing problem with the connection, but I'm sure if it's still buffering, we are gonna try and see the recording if it will be good enough for you guys to see what we've been doing. Then that will be fine. But if it still shows with some glitches and hiccups, we'll have to make a redo of this session. So do not worry much. Anyway, we're on question number we're on question number 1.5, at which point we were looking at the work done in by a force in increasing the velocity from 0 to v, being w. That is the work done on an object, and the net work done by the same force F on the object to increase its velocity from v to 2v. So now if we want to find the work done, we'll call it unknown work wx, in changing the velocity to from v. So this is half m 4v squared minus half m v squared, which is equal to 3 times half mv squared, where half mv squared is w. So this new work done by the force in changing, remember this is w, v to 2v will be equal to 3w. Remember the work done is equal to the change in the kinetic energy, and in this case the kinetic energy is changing from half mv squared to half m times 2v all squared. What we're squaring is 2v to get 4v squared, and so 4v squared minus v squared, why did I put cubed there, will be equal to 3v squared, and half m of v squared times 3 is 3w. 3w is the net work done by the same force in changing the velocity from v to 2v. Okay, so D is the best choice there. The best choice is D. This question on redshift, maybe I'm gonna leave it there. We'll discuss more on frequency so that we don't mix up a lot of this. Oh. So my screen, what happened to my screen there? I can't see anything. Okay, so this is what I was explaining. The work done, the unknown work done in changing the velocity from v to 2v will be the change in the kinetic energy, where the final kinetic energy is half m times 2v all squared minus half mv squared. So you do the mathematics there, you would find that the other one is 4 half mv squared, the other one is half mv squared, which is 4w minus w. And that gives us 3w for our answer, and that's how we got to D. So that's how we got to D. Then let's see what our next question would be. Not electricity, not that, 2 blocks. We'll look at these ones on friction again, and second, the Newton's second law in our next, in one of our, today we just want motion under gravity. So we have a learner drops a ball A from a height 8 meters. So there is the guy to the left. He drops a ball A from 8 meters above the ground. Then after 0.6 seconds, another learner throws a second ball B downwards from the same height. Now this one is thrown. The first one drops, the other one throws. So check note. Now both balls A and B hit the ground at the same time. Ignore the you can see the thrown ball has got some effect on it, or like it starts with the velocity, high velocity there. Okay, so define the term free fall. Free fall is one in which the force of gravity is the only force acting on it. So the only force acting on an object is the force of gravity. When an object is said to be in free fall, the only force acting on it is the force of gravity. So now the second part. Okay, so we have free fall as the first part. Keywords: only force is the force of gravity or gravitational force. So there's only one force acting on it, and it's the force of gravity. And calculate the speed at which ball A hits the ground. Okay. So we have which equation do we use? We've got a number of equations we can use there. We have a number of equations to use. And what are we given? We cannot use any equation with t because we don't have time in this question. We only have the displacement 8 meters, then the time when or the delay time between when ball A and ball B were allowed to be in free fall. Okay, so if we have what else do we have? We know we've got acceleration. So with acceleration and displacement, we can find the speed with which A hits the ground. So which means we can use this one, v2 squared equals to v1 squared plus 2a delta y. Okay, so what have we done here? We've chosen our downward direction to be positive. Downward is positive, so if downward is positive, it would mean A is positive 9.8 meters per second squared. It would mean delta y, the displacement, is minus 8.0 meters. Why? Because they are starting from above the ground going in the negative direction. So delta y becomes negative. So this is because we have assigned the downward direction to be positive. So now v2 squared, what else do we know? V initial, v1 is equal to 0 meters per second. So v2 squared equals to 0 plus 2a 9 minus 8. Did I choose right? Did I choose right? Did I choose right? Zero. Downward is positive. A 9.8. Did I say downward is positive? Okay. So if downward is positive, okay, we didn't say it's negative. Downward is positive, it's okay. Downward is positive like that. So which means 0 is at the top. So displacement should be positive 8. Sorry about that. Displacement should be 8. So if we're starting from the ground and we're going upwards and the downward is positive, that's when we give the direction to be negative for the displacement. So in this case, we're just going downward and the displacement is in the same direction as the positive direction, which is the downward direction, so it has to be positive. So now that means our V2 will be the root of 16 by 9.8. Let's see if we can calculate this one together. I know you guys by now you know how to use a calculator, so that should be a simple calculation. There is the calculator. Like that. So that's the root of, open bracket, 16. 2 times 8 is 16 by 9.8. 12.5. So that's the root of 16 times 9.8. I don't know what that product gives you, but it says V2 is 12.5 meters per second. So the velocity with which A hits the ground, or A reaches the ground, is 12.5 meters per second. Then ball B was thrown downwards, the speed at which ball B was thrown downwards. So to continue, we already know the speed with which A reaches the ground, so we can determine time using that speed. That time will help us find the time at which B reached the ground. So still for A, the time V2 equals to V1 plus A delta T, right? Where V2 is the final, which is 12.5. We said downward is positive, we're maintaining that. So we're using 12.5 equals to 0 plus 9.8 times delta T. Then we divide 12.5 divided by, so it is that divided by 9.8. 1.28 seconds. 1.28 seconds. Okay, so it means delta T equals to 12.5 divided by 9.8, which gives us 1.28 seconds. So 1.28 seconds is the time it takes for ball A 8.0 meters so to reach the ground. So it takes 1.28 seconds, and its velocity at that point is 12.5 meters per second. Then we have another ball, ball B, which is thrown with an initial velocity V1 for ball B. Then it goes down, reaches the ground with the velocity V2, and it arrives at the same time. So by the time it arrives, its time, so here delta T is that, but its delta T is equal to 1.28 seconds minus 0.6 seconds, because it is launched 0.6 seconds later. So its delta T will be 0.68 seconds. Okay, so which means we have the displacement delta Y, we have the time for object or for ball B. We don't know these two velocities, but we also have gravity as 9.8. So the question says the velocity or the speed the speed at which the ball is thrown downwards. So we want v1. We want v1. So what is that initial speed which will make v1 reach the ground or cover 8 meters in 0.68 seconds? So the equation that we can use there is the more interesting one, which says delta y equals to v1 delta t plus half g delta. So we have delta y, which is the 8 meters. What else do we have? v1 is what we're looking for. Delta t we have, g we have, and that. So which means we can find v1 should be the only unknown in the expression. So 8 meters equals to v1 times 0.68 plus half. Remember I said going downwards is positive, so that's why we are simply using 9.8 there. And v1 is downwards, is positive. Delta y is also positive downwards, so they're all in the same direction. So 0.68 squared. So if we calculate, let's see what the calculator gives us. Half of 9.8, that's 4.9 times 0.68 squared. So open bracket. .9 times 0.68 squared, 0.68 squared, close bracket, and it's 8 minus that, so it's 8 minus all that which is in the bracket, that, then that's 5.73. Okay, so 5.73, then we divide that. So what we are doing here is 8.0 minus half of 9.8 is 4.9 multiplying 0.68 squared. Okay, equals to v1 times 0.68. So divide by 0.68 everywhere, we get v1. So this equation over 0.68 gives us 8.43. It gives us 8.43. v1 equals to 8.43 meters per second. So it says speed, we don't need to give direction. This is just the speed with which ball B is thrown downward. So ball B starts with an initial waves ball B there. We found the answer there. This is 8.43 meters per second downwards. So we found that one by using the times. So having done that, so that's 5 marks for that question. You have to be very careful what you do there. So your reasoning should be based on the two balls, right? So which means the time which ball B traverses is 0.6 seconds less from the point when it's thrown. That time will be 0.6 seconds less than the time with which A reaches the ground. So based on that, you already have the time for ball B, you already have the height for ball B. So with time given and height moved, knowing G, we can find the initial velocity with which it is thrown or released. Released is not the proper term. So it's thrown. You have to be careful of thrown. Okay. So with that in mind, you'll be able to find the initial velocity for P. The ground to a maximum height of 6.5 meters above the ground. So there we have ball A bouncing off. So we're done with this ball B story. Now we go back to ball A. So ball A bounces off. That's ball A to a maximum height of 6.5 meters from the ground. Calculate the velocity of ball A as it bounces off the ground. Okay. So now V1 for A, we're dealing with A. V1 is equal to something we don't know, but V2 is the final. It will be T. Acceleration is now. We'll maintain again. We said downward is positive. Did we say that? Did we say that downward is positive? We said that here and maintained the same throughout. Downward is positive. So now it's going up. So A is minus 9.8 meters per second squared. What am I saying? Downward is positive. A is still the same, 9.8. But V1 is negative because V1 is going up. V1 will be negative. Our displacement delta y upward, it's minus 6.5 meters. So you see what we stance you want to take with regards to directions, you have to maintain throughout so that your equations have some consistency. So in this case, we say it downward is positive. So the ball is going up. So its initial velocity will be negative. Gravity is positive, which is correct. The displacement delta y is also negative because it is moving upwards. It is displacing upwards. Okay, so for us to find the velocity V1, we can use V2 squared equals to V1 squared plus 2a delta y. V2 squared, did we say we know it's 0? V1 squared, even if it has a negative there, so that's what we want to find. Then 2 plus 2 times 9.8 times negative 6.5. This is cool because it means we're just finding the root of 2 times 9.8 times 6.5. So if we take this whole thing to the other side, it's positive, and V1 squared remains there, positive. If we take the square root, then we only have V1. So the root of 13 times 9.8. The root of 13 multiplied by 9.8. 13 multiplied by 9.8 is 11.29. 11.29 meters per second. Do not forget your units, guys. Do not forget your units. So we have 11.29 meters per second upwards. So remember, we said V1 is negative. So we could put a negative there, negative 11.29, because this is the root of this is plus or minus. So our solution in this case is 11.29 meters per second equals to V1, meaning it's just 11.29 meters per second. You can state the negative means upwards. The negative means upwards. Okay, so you can leave your negative because you have defined positive magnitude and give the direction to say it's upwards. But in either way, for you to get full marks, you need to state both magnitude and direction. So this is acceptable. This is also acceptable. All right. This was part 3.3. This was an answer to part 3.3. Part 3.4 requires us to make a sketch. Let me use another black color. Sketch velocity versus time graph for the motion of the ball from the which is its maximum height after the bounce. So it's a sketch. Velocity. So this is velocity in meters. No, I don't want to put it like this. Velocity in meters per second. And this will be zero velocity. Then velocity versus time for the motion of ball A from the moment it was dropped. So it was dropped at, with a velocity of 12 point, no, of 0. Ball A was dropped with a velocity of 0 and increased to 12.5, then bounced off with an initial velocity of 11.29 upwards. Okay. So if this is 12.5, then after 1.28 seconds, which is there, 0.28 seconds. Okay, something like that. So that's 1.28 seconds. It reaches a velocity of 12.5. This is when it hits the ground, so it bounces off. It bounces off. This happens in a few seconds. Then at 11.29, 11.29 meters per second, it leaves the ground to a maximum height again. Like that. Don't know what that time is, but this is at 11.29 meters per second. So indicate the following on the graph: the velocity with which the ball A hits the ground. So here it hits the ground. Then the velocity with which the ball bounces off the ground. Bounces off the ground. So it hits the ground with a positive velocity and bounces off the ground with a negative velocity, which is upwards. So this was downwards, this is upwards. So at this point, downwards, and at this point it's upwards to 0. So it comes back to 0 at that point. So this is at it starts from a maximum height at 8 meters. This time it's 6.5 meters at its maximum height. It's always 0 at those points. So this is how we present the velocity time graph for a bouncing ball. A bouncing ball dropped from a certain height above the ground. Okay, so that's a collection of some 17 marks for you on such type of a question. I hope this has been helpful enough. In our next session, we'll look at another set of interesting questions. There's this question on a falling brick, and it's a question on momentum. So we would want to look again at such a question and apply what we have learned so far. So I'm gonna leave it here. It's that's all we had for today. I hope you'll be able to receive every bit and piece of each part of this video. Unfortunately, the video should have had a lot of buffering in the live stream. So if the recording also comes with the same buffering, we'll have a redo of this session and try to interact more with regards to what we covered on today's session. So without further ado, I'll just leave it here, guys. Have a blessed night and have a great week ahead. From me, James, and everyone here at Yebo Tutor, we love you all. Stay blessed and bye-bye.